Welcome. In this video, we will provide a brief overview of the IQScope software. The IQScope software runs on either your equivalent time oscilloscope or on a standalone PC. If it's running on a standalone PC, you can still communicate to the instrument, take measurements in real time if your instrument is connected to the PC using a GPIB connection or through your existing Ethernet connection. So here's the software. The main window is showing 4 graphs that can visualize the information, as well as the toolbar on the top. If we click on the New Measurements icon, you can either load an existing file or connect to a scope to perform new measurements. So now the IQScope is searching your existing connections to identify any potential oscilloscopes that are compatible with the IQScope. So now that we have identified an Agilent 86100D, which is compatible with the IQScope, we'll just go ahead and select that. The setting window pops up. This lets us control the current measurement conditions. You can switch between pattern mode and eye mode. Total number of samples is shown, so we will measure 400 BAUDs in this case, and we'll do 10 samples per BAUD, providing 4,000 samples. The baud rate of our source is 28 gigabaud. Set the start time to 3e-8. So that calculates our time range automatically from the baud rate and the number of BAUDs. And we'll select the modulation format of our transmitter. In this case, it's QPSK. We could select BPSK or 16 QAM, as well as dual pole modulation formats if our transmitter is configured with those modulation formats. Under the trigger window, you can configure the trigger to your sampling oscilloscope. So we know the clock divider is a 64 clock divider, and the current pattern length is entered here. Now the X-pole and Y-pole mapping let us map the logical channels to our physical channels on the oscilloscope. Since we're only doing a single pole channel measurement, rather the Y-pole mapping is disabled. So we'll go ahead and accept this. So now we're ready to start our measurement. So we'll go and click on the Continuous Acquisition button, and the measurements will begin. So here we can see our 4 visualized graphs. We've got our X-pole constellation, which is just showing the cluster of symbols. We have our vector diagram, which is showing the symbols and all the transitions from one symbol to the next. Our EVM graph on the bottom right-hand corner, as well as the X-pole eye diagram for the eye projection, in-phase projection of our signals. So by clicking on the top of any one of the graphs, we can change what we're visualizing. Anything from eye diagram traces to pattern plots to different IQ plots, as well as the frequency spectrum of the signal that we're measuring. You can also change how many graphs you're visualizing. So if you wanted to switch between 2 graphs or 3 graphs, or reconfigure how you're visualizing any of the information, you can easily do so on the top. You can zoom in to any portions on any graph and get some more detailed information. By right-clicking on the graph, you can change the auto scale parameters as well as save any particular graph. You can save bitmaps, or you can save it to CSVs or XML formats. So if we go to the top and click on X-pole constellation, we can switch to some pattern plots so that we can see the detailed information on the in-phase and the quadrature time traces. So let's switch to a 2-graph view mode. So on the top, I'm showing you the in-phase information, and on the bottom you're seeing the quadrature information. So here we can see the binary data that we are transmitting on each of the in-phase and quadrature. We can zoom into any of those sections. Or alternatively, we could show the intensity and the phase information for our complex modulation format, in this case QPSK running at 28 gigabaud. So let's switch back to our foregraph view mode now. And let's switch back to our constellation plot and our vector diagram. So now a common way of showing the quality of your transmitter is by using the EVM measurement. So the EVM measurement is typically a waterfall or a bathtub curve. So you get the lowest EVM in the middle of your bit symbol, and as you move away from your bit symbol, your EVM goes up, and as you move back to your symbol, your EVM goes back down. So it shows you this bathtub curve. We can get some more detailed, specific information on our transmitter if we click on the title bar on the right. So this shows us the measurement information. So we're running at 28 gigabaud. We've got 10 samples per baud, and our modulation format is QPSK. So in this case, we see that we have a slight RF imbalance of about 1.5%, a pretty good quadrature error in the range of 0.6 degrees, small bias errors in the 2% region. We also are identifying an IQ skew, so a timing skew of about 1.5 picoseconds between the I and the Q channel. And you can see also the EVM. The number that we're particularly interested in is the EVM at the symbol, and that's currently about 9.7% at the symbol period in RMS. So we can choose all different types of visualizations. You can show our 4-level phase eye diagram. You can also show our intensity eye diagram that we're familiar with when we're usually looking at our scope traces for a QPSK signal. So let's choose intensity. So there's a typical intensity eye diagram for a QPSK signal. So that is a quick summary of how you would use the IQScope software. For more information, please go to southernphotonics.com and visit our website as well as our other instructional videos on the IQScope.